Hello. Okay, so I decided to record this part of the video just because I thought this was pretty important. It kind of summarizes all the things that we've kind of gone over in the past year. So here are just some examples of how we can model linear, quadratic, and exponential functions. So a linear model is something like a scatter plot. You try to find a line of best fit, right? So the equation for that would be y equals mx plus b. For a quadratic equation, right, we learned that this would be like y equals ax squared plus bx plus c, something like that. And we know for an exponential model, if you guys were did the other assignment right before, or if you're just following my notes, this is y equals ab, and we're raising it to the x power. So a linear model creates a straight line. A quadratic model creates this kind of like U-shaped kind of curve. An exponential function, so this is what we learned recently, so it has this shape, but it doesn't really go back up. Okay, rises or falls quickly in one direction. Okay, so another thing I wanted to mention is I'm using my phone for this rather than a computer video, so I apologize if my phone decides to get a little blurry at times, but I think it'll be okay for the purposes of this video. Okay, so for the first example, we're going to determine whether each scatter plot would fit a linear, quadratic, or exponential function. Okay, so if I look at this data here, if we look at this data, if we try to look at the type of line or the type of curve that is created here, right? So if we look at this, it's creating this U-shape type of curve. So this, a model that could best represent this would be a quadratic function. So quadratic function. If you look at this one kind of looks like this one here. But yeah, so it just kind of looks like it's going somewhere and it goes back up here. So this, although it looks linear, it's actually more curved. So this would represent an exponential function. So exponential function. Okay. If you look at this graph, you can draw a nice line right through all those points. If you can draw a nice line between all those points, that was related to creating a line of best fit. So that means this must be a linear model. Okay. So not too hard, but hopefully you guys can figure it out. But okay. So next part I want to go over is what if you had a table? So what if instead of giving you points like this, what if you had a table instead? So if you have a table instead, for a linear function, you might have learned this in Algebra 1. So you never see the same y value twice, and the first difference is the same. So I'll describe what that first difference is. So if you look at the difference between this number and this number, you would add 2 to get to the next number. If you had to compare 1 and 3, you have to add 2 to get to the next number. If you look from 3 to 5, you also add 2 to get to the next number. This is considered the first difference. That's the first difference, if you're wondering what that means. Okay, for a quadratic function, you might see the same value, y value, more than once. So if you look at this plot here, there's probably some y values that repeat, even though the x values are different. And the second difference is going to be the same. So the second difference, I'll go and describe that. So let's say we compare the differences between all these numbers. So if we compare the difference between 1 and 0, we would subtract 1. If you want to compare the difference from 0 to 1, you would add 1. The difference from 1 to 4, you would add 3. The difference from 4 to 9, you would add 5. Okay? Next, so this would represent the first difference, right? This represents the first difference. Now, in order to find a second difference, we would have to find the difference twice. So we found it once between these numbers, and then you'll find it twice. Okay, so the difference between -1 and +1 is 2. The difference between 1 and 3 is going to be +2. The difference between 3 and 5 is going to be +2. This represents the second difference. The second difference is going to be all the same. So that means you would have a quadratic function. Okay? If you have an exponential function, you're trying to look for a pattern with a common multiplication pattern in the y values. Now, if you tried to look at these ones, at these y values here, you wouldn't be able to find a common multiplication pattern. If you look at these y values, each of these values are going to multiply by 2. And this would represent that common ratio b that I mentioned in the other set of notes. So that would be b. So your common ratio would be 2. So yeah, you look for a common multiplication pattern, and you never see the same y value twice. None of these y values are the same. Okay? Alright. So what I'm going to show you next is another example. So okay, so does the table of values represent linear, quadratic, or exponential function? Okay, so if we look at this, what I see here is that if you try to find the common difference between all these numbers, you would add 6, you would add 18, it would get kind of crazy. So that might tell you maybe it might be a pattern of multiplication. If you do that, if you just do 9 divided by 3, the common ratio b would be 3. So if you just did that, 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And 81 times 3 is 243. So because we see a common multiplication pattern, we see a common multiplication pattern here. This would represent an exponential function. Okay? Now, you could try the same thing with this if you wanted to. You might run into problems if you try to think that's exponential. What I immediately see here is the difference between 21 and 17 is -4. You would subtract 4 to get from 17 to 13. You would subtract another 4 to get from 13 to 9. And you'd subtract another 4 to get from 9 to 5. So the common differences are all the same. So since all the common differences are all the same, this is going to represent a linear function. Okay. Now, this last one, usually if you see repeated values in the y's, you might, just want to consider that's going to be quadratic. But let's go and prove that. So 19 minus 7, the difference between those is -12. Difference between 7 and 3, -4. From 3 to 7, you add 4. And from 7 to 19, you're adding 12. Okay, that would be the first difference. Okay, then if you want to find a second difference, so 12, between -12 and -4, you would add 8. From the difference between -4 and +4, you'd also add 8. And from here, you'd also add 8. So you see here, this is our second difference, right? So since our second difference, all the numbers are the same, this is going to represent a quadratic function. Okay? Right. So let me know if you have any questions on that. I'm going to do the last part. Okay. So during this quarantine crisis that we are going through, I just decided, I'm just going to try plot some values. So let's model this the coronavirus case count in Hawaii in the last 20 days. So I took this data from April 3rd and a couple, like 20 days before that. So if I use technology, I can actually use a computer that generates an exponential function for this. So it would be modeled by that equation, and that is represented by this smooth curve that you see here. Okay. So the first question asks, is the function linear, exponential, or quadratic? So if you had to look at our little cheat sheet here, if you had to look at all the coronavirus case data that we have done recently, it would most likely look like an exponential function. It's exponential growth, and that's what's happening if we aren't flattening the curve and we all just go out to just not social distance and stuff. But anyway, this would be an exponential. So this would be an exponential function. Okay, so the next part, so it says using the points 1, 5 and 2, 8, you want to create an exponential function from the given points. So what I see here is that we're using these points here. You see these points? We're using 1, 5 and 2, 8. So from these points, in order to, what we need to first do is we need to find our common ratio. So in order to find our common ratio, if you guys kind of paid attention to the video before this, you take the second y value and divide it by the first. So it's going to be 8 divided by 5. And if you do that, that's going to be 1.6. Okay. Next, what we want to do is we want to choose any point. Choose any point, and our goal is to use this basic equation in order to create an exponential function. So I'm just going to make it easy. I'm going to use this. This is my x, and this is my y. So y is the same thing as f of x. So what we're doing is we're just plugging it in. So this is 5. A is what we're solving for. B is 1.6. And we're raising it to the first power because x is 1. Okay. Now, 1.6 to the first power is going to be 1.6. So this is going to be 5 a multiplied by 1.6. Now, a times 1.6 is the same thing as 1.6 multiplied by a. Okay. So next, what we need to do is, if we were to calculate this, we want to solve for a. So you just go 5 divided by 1.6. So it's going to be 3.125. So a is going to be 3.125. We need this parameter, we need b, and we need this parameter a in order to solve for, in order to create our exponential function. So we know that our exponential function is f of x equals a times b raised to the x. Okay, so what we're going to do is we're just going to plug in all those values that we know. So this is going to be f of x equals 3.125, goes in here. B is going to be 1.6 and raising it to the x. So that would be our exponential function equation. Okay, now next part. So it says, are our results close to this? So earlier in the problem, you see here, this is our equation that we started with. Are results close to this function? So we're comparing our y equals 3.125 times 1.6 raised to the x. Are our results close to this or not? And if you look at it, it's not. Yeah, not close. And what do you think we could do to improve the accuracy of our data? So generally what you want to do is you want to look for points that are near the curve. So for example, that you could choose this point and this point, you could choose this point and this point, and so forth. These are not as close to the curve, so that's why these points did not give us something that's close to what the computer gave us. Okay, so it's not close. So one way that we could improve, so what could we do to improve the accuracy? So one thing that we could is we could choose 2 points that are closer to the curve. So that's basically how you would answer that one. So let's go ahead and do that, which is what I modeled for you in letter D. So in letter D, so instead of choosing these points, what if we chose these two? So that's the points 18, 225 and 19, 259. Okay, so I want to create an exponential function from those given points. So what I see is that our ratio is going to be 259 divided by 225. And let's see what that is, because I don't know what that is at the top of my head. So let's see. 259 divided by 225. So it's going to be 1.1511. Yeah, 11. I'll just put that there. Okay. So next, what we need to do is we need to identify an xy value. So just any point. I'm just going to choose this one. This one looks easy. This is my x, and that's my y. Okay? So we're going to use that same equation. F of x equals ab raised to the x. So I'm just going to round this. I'm just going to put 1.151. Actually, well, first, yeah, a. So 1.151, just to make it easier. And then this x is going to be to the 18th, raised to 18th. Y, our output, is going to be 225. Now, I do understand that some of you do not have the calculators in class to be able to do this. So one way that you could do it, you could do 1.151 times 1.151 times 1.151, and just keep multiplying it over and over and over until you hit 18 times. Or another way that you could go about doing it is you could use Desmos. If you use Desmos here, you could also calculate that value, right? So I'm just going to put that value in, okay? So 225 equals, so it's going to be 12.59, let's go with 12.59a. Yeah, so that's just this raised to 18th power. Now what you want to do is if you divide each side by 12.59, right? 12.59 divided by 12.59. This means that our answer, so 225 divided by 12.59, it's going to be about 17.87. So 17.87. I'm just going to keep that last thousandths decimal place. So 17.871. Okay. So we know A. We know A here. And we also know B. We need these two parameters in order to create our equation. So our equation, a basic equation for exponential function is f of x equals a times b raised to the x. So leave f of x and x alone. Just touch the parameters. A is 17.871. B is our common ratio, 1.151. We're raising it to the x. Okay. Now, the last part. So let's look at this now. So now our results this time closer to this function. Now, if you had to look at it, of course, yeah, you look at that 17.871. That, unfortunately, that wasn't as close, but the ratio is close enough. If you want to consider where that is, if you're wondering, like if you, let's say you plug a 0 into here. So that means the y-intercept is going to be at about 15 based on the computer model. You're saying the y-intercept here based on your hand calculation would be about 17.87. If you think about it, this the coronavirus cases in Hawaii, it's a really big graph. It's a really big graph that goes to almost 300 something cases with yeah, about 300 cases. So what this actually means is that this is actually not too far off, I guess, compared to the entire data. But this time our results are closer, so we can say it's closer. Yep. So it's closer, and the reason why it's closer is because we decided to choose some points that were near the curve. Okay. All right, and that's pretty much it. So please let me know if you have any questions on this, and then I'll continue that last video if you guys need help on that. Okay, thanks, bye.